ready to tackle the Big Bang. Yeah, I know. It's one of those things, one of those topics that can kind of make your brain feel like it's doing cosmic gymnastics.
Hmm.
But
Yeah.
hey, that's why we're here, right? To break down these incredible notes you've gathered and uncover, like, the most mind-blowing bits about the universe's origin story. Where do we come from? How did it all begin? All that good stuff.
And trust me, you've got some fascinating details in here. It's really amazing how much we've learned, just even in the past few decades,
Right.
but also how many questions are still swirling around out there.
Yeah, exactly. It's like every answer just leads to more questions, which I kind of love.
Mm-hmm.
But you've got all these details on the Big Bang itself, right?
Yeah.
But before we dive into like the nitty-gritty, I kind of want to take a step back for a second.
Hmm.
Imagine trying to understand the universe before we had telescopes, satellites, all that jazz.
Right.
People were crafting creation myths.
Right.
Stories about gods and monsters and
It really highlights how radical the shift to scientific thinking was. Suddenly, we weren't just telling stories, like we were searching for evidence, for a way to explain the universe through observation and measurement.
evidence.
Yeah.
Hard facts, as much as we can get them at least.
Yeah.
And that's where the Big Bang comes in, right? This idea that's like grounded in, well, a lot more than just like someone's imagination.
Yeah.
But I have to admit, when I hear Big Bang, my brain, like, it still kind of pictures this massive explosion, like a firework gone cosmic.
Right.
But these notes set me straight. It's not an explosion at all, is it?
Not even close. Think of it this way. Imagine a balloon, right, with dots all over it.
Okay.
You start inflating it, the balloon itself, that expands, right? The space between those dots, that grows. But the dots themselves aren't moving across the surface.
Okay, I'm with you so far.
The Big Bang is like that, the expansion of space itself.
Whoa.
Everything moving further apart, stretching out from an incredibly dense, hot starting point. And here's the kicker, that expansion. It's still happening.
Wait, so everything is constantly moving further apart?
Right.
Like, as we're sitting here, everything is getting more distant?
Exactly. That's where Edwin Hubble's observations come in. He was looking at galaxies, right? And he noticed that they're all moving away from us.
No way.
Even weirder, the further away a galaxy is, the faster it's moving away, like a cosmic acceleration.
Okay, that does sound pretty convincing.
Huh.
But we need more than just fleeing galaxies to prove something as massive as the Big Bang, right?
You're right, one piece of evidence isn't enough to rewrite our entire understanding of the universe. Luckily, we've got more. Remember reading about the discovery of the cosmic microwave background radiation?
Yes.
The CMB?
CMB definitely doesn't have the same ring to it as Big Bang, gotta say.
Right.
But from what I gathered, this discovery was a total fluke.
Pure accident. These two scientists, Penzias and Wilson, they were trying to get rid of this annoying static in their radio antenna. Turns out, that static was actually faint radiation coming from every direction in space.
No way. They discovered the echo of the Big Bang because of bad reception.
Essentially, imagine it like this. You know that flash of light after a really intense explosion? Think of the CMB as that afterglow, except it's been traveling through the universe for almost 14 billion years.
That's incredible. So what can we actually tell from this ancient light? What's it like? What's it saying to us?
Well, the CMB is incredibly uniform, meaning it looks almost the same in every direction. That supports the idea that the universe began from a single point. But here's the thing. There are also these tiny, tiny variations within that uniformity, like ripples on a pond.
Ripples, you say. What do those tell us?
They're actually crucial. Those subtle variations in the CMB represent tiny differences in density in the early universe. Think of them like seeds. Those minuscule variations eventually grew into the large-scale structures we see today. Galaxies, clusters of galaxies, even you and me, we wouldn't be here without those initial ripples.
Okay, so that's expanding galaxies and leftover light from the very beginning. What other evidence did you uncover in your research?
You're in for a treat. Remember those notes about the abundance of light elements in the universe? Like a cosmic recipe.
Right. Hydrogen and helium, all that good stuff. It's like, what's the universe made of?
Exactly. Imagine the universe in its earliest moments, like so hot and dense that only the simplest elements could form. Hydrogen, a dash of helium, and a pinch of lithium. Those are your starter ingredients.
So these are like the OG building blocks of everything.
Precisely. And get this, the Big Bang Theory, it doesn't just say, oh yeah, these elements should exist. It predicts the exact proportions we should see in the universe today, billions of years later. And guess what?
Don't tell me.
The predictions line up perfectly with what we actually observe.
Okay, that's pretty wild. It's like the universe left us a recipe card, and it's all there, measured out perfectly.
A recipe card written in the language of stars and galaxies. Speaking of which, your timeline goes into some pretty wild territory.
I know. Talk about a wild ride.
Yeah.
We go from a universe, like, smaller than an atom to, well, us. I gotta admit, some of it makes my head spin. Maybe we can hit the highlights.
Absolutely. Okay, so picture this. We're talking fractions of a second after the Big Bang,
Okay.
an era called the Planck epoch. Imagine the entire universe crammed into a space smaller than an atom.
Okay, now my brain is officially fried.
Oh.
How? How is that even possible? How can something so vast be so tiny?
It's almost impossible to wrap our minds around, but that's the thing about the Big Bang. It constantly pushes the boundaries of, like, what we thought was possible.
Hmm.
During the Planck epoch, our current understanding of physics it dissolves. It's a realm where gravity and quantum mechanics, the forces that, govern the universe on vastly different scales, they're thought to have been all intertwined.
Okay, so how do we get from a universe smaller than an atom to, well, everything we see today, all the stars, the planets, even just the space for it all to fit?
Right. That's where things get even more mind-blowing. Buckle up for the inflationary epoch. We're talking about a period of ridiculously rapid expansion, and I mean rapid, in the first fraction of a second after the Big Bang.
Wait, hold on. Faster than the speed of light fast.
You got it. Now, I know what you're thinking. It sounds like we're breaking some fundamental rules of physics, but the evidence for this period of inflation is incredibly strong, and it helps solve a big cosmic mystery. Why does the universe look so incredibly uniform on a large scale?
Right, with the same temperature everywhere, even though some parts are billions of light years apart.
Exactly. It wouldn't make sense if the early universe just expanded at a normal pace. But with inflation, that tiny, incredibly dense universe could balloon outwards so rapidly that it essentially smoothed itself out before any major differences could develop, like stretching out a wrinkled piece of fabric.
Okay, so it's like ironing out the universe. Got it. I think I'm starting to grasp this whole inflation thing, as much as anyone can, I guess. But this smooth, inflated universe, it isn't exactly teeming with stars and galaxies just yet, right? What happens next on our cosmic timeline?
Right. We're still missing some key ingredients for stars and galaxies and planets, but those ingredients need the universe to cool down a bit first, Gotta let that cosmic soup simmer for a bit.
So like letting the cosmic soup simmer? I like that. What are we making? What's in the soup?
Well, this is where recombination comes into play. About 380,000 years after the Big Bang, the universe has cooled enough for electrons, those tiny negatively charged particles, to combine with protons, the positively charged ones.
Okay, they're forming atoms, right?
Exactly. They're forming neutral hydrogen, and that changes everything.
Okay, and that's significant because...
Imagine the early universe as a dense fog. Light couldn't travel very far because it kept bumping into all these free electrons. But with recombination, think of it like the fog suddenly clearing.
The universe goes from opaque to...
transparent. Light was free to travel, and it just kept going. Some of it reaching us billions of years later as...
the cosmic microwave background radiation. So that afterglow we were talking about earlier, it's all connected.
You got it. We're literally looking back in time, witnessing the universe becoming transparent, all thanks to those electrons and protons finally getting it together.
Now that is a glow up for the universe. So we have the expansion slowing down a bit, things cooling down, light is finally able to travel freely. What happens next? I can't wait to get to the stars forming.
Get ready for gravity to take center stage. It starts pulling matter together. Those tiny density fluctuations in the early universe we talked about, they start to become more pronounced. Remember those ripples in the cosmic pond?
Yeah.
Now they're forming waves.
Leading to the first stars and galaxies. And I feel like we could do a whole separate deep dive just on that process. I bet those first stars were absolute behemoths.
Oh, absolutely fascinating. But I think for now, the important point is that this era marks a really fundamental shift. We go from a universe dominated by radiation, like that afterglow of the Big Bang, to a universe dominated by matter. It's the beginning of structure formation, of the cosmos as we know it.
So we've covered like billions of years of cosmic history here. From a tiny speck, smaller than an atom, to a universe that's, well, teeming with stars and galaxies and, us.
Right.
But what happens next? I mean, the research you've gathered, does it say anything about the ultimate fate of it all?
That's where things get a bit hazier, to be honest. It's kind of like trying to predict the weather billions of years from now.
Right.
There are a lot of factors at play, many of which we're still trying to understand.
Okay, so less of a cosmic crystal ball and more like a choose your own adventure for the universe. I can dig it. So what are some of the options on the table?
Well, your notes mention a few really intriguing possibilities, like the big freeze,
Okay.
the big crunch,
Yeah.
even the big rip. Cosmologists really know how to coin a catchy term, don't they?
Well, hey, it gets the people going. Okay, so big freeze. What are we talking about there? What would that look like?
Imagine, like, the universe keeps expanding just like it is now, but over incredibly long periods, things just keep cooling down.
Okay.
Stars burn out, galaxies drift farther and farther apart, until eventually even black holes, they evaporate, and you're basically left with this vast, cold, incredibly empty cosmos.
Yeah.
A little bleak, I'll admit.
Like a cosmic ice age. Not exactly the most exciting ending to the story. What about the big crunch? Is that any better?
That one's basically the opposite of the big freeze.
Okay.
Imagine the universe's expansion. It starts slowing down, right?
Okay.
Comes to a halt and then reverses.
Whoa.
Everything gets pulled back together by gravity until we're right back where we started, that incredibly dense, hot singularity.
So it's like hitting rewind on the Big Bang. Will we, like, go through the whole thing again? Another Planck epoch? Another round of inflation?
Some theories suggest exactly that. A cyclical universe constantly expanding, collapsing, and then being reborn. Talk about deja vu on a cosmic scale.
That is some serious food for thought. But all right, you mentioned one more, the Big Rip. What's that all about?
This one's a little more intense. Remember we talked about dark energy? That mysterious force that's pushing everything apart?
Right, like the cosmic fuel behind the universe's expansion.
Exactly. Well, in the Big Rip scenario, dark energy, it gets stronger over time, and eventually it just overwhelms the force of gravity.
Oh, I don't like the sound of this.
Yeah, it's not pretty. Galaxies would be torn apart, then stars, then planets, even atoms themselves. It'd be the ultimate cosmic shredding event.
Okay, definitely not how I want the story to end. It sounds like the fate of the universe is still very much up in the air, literally. But even without knowing the ending, this whole journey through the Big Bang, it really does bring up some pretty wild questions, doesn't it? I mean, where did that initial singularity come from? That infinitely small point. What existed before the Big Bang? Was
Right.
there even a before in the way that we understand time? These are things I think about in the shower.
Mm-hmm.
And I was struck by something in these notes that you dug up, this idea that maybe, just maybe, the Big Bang points to, like, something beyond our current understanding, something that sparked the whole thing, something outside of the universe as we know it.
It's a question that has haunted physicists and philosophers for centuries.
Right.
While the Big Bang Theory explains how the universe evolved from that initial state, it doesn't necessarily tell us why it started in the first place.
It's true. It's like we've come so far, but we still don't know.
I love it. Okay, before we, spiral into an existential black hole here,
Right.
how about a quick recap? We dove deep, deep, deep into the Big Bang. We learned that it's not an explosion, but the expansion of space itself, which is still blowing my mind a little bit, if I'm being honest.
And we looked at all this incredible evidence, right? We've got galaxies racing away from us, that ancient afterglow of light from the CMB, and even, like we were just talking about, that precise cosmic recipe of those first elements, hydrogen, helium, little lithium.
Yeah, all pointing back to this incredible event nearly 14 billion years ago that set the universe we know and love into motion.
We traveled from a universe smaller than an atom through periods of, like, mind-bogglingly rapid expansion, those first flickers of light, the formation of stars and galaxies. We even pondered the universe's ultimate fate. It will be a big freeze, a big crunch, a big rip.
Yeah,
I don't know about you, but it's been a wild ride.
it has.
But I think the biggest takeaway for me, at least, is just the sheer awe of it all. I mean, the fact that we can even begin to comprehend these events that happened billions of years ago,
Right.
that we can use science to piece together the story of our universe. I mean, that's truly remarkable.
It really puts things in perspective, doesn't it?
It really does. And here's the thing. As mind-blowing as all of this is, I have a feeling we're only just getting started, right?
Mhm.
What if our current understanding of the Big Bang is, like, just the tip of the iceberg?
I like where you're going with this.
What if there's a whole other chapter to this cosmic story that we haven't even begun to imagine? Something even more incredible, even more awe-inspiring, something that completely reshapes our understanding of where we come from and where we're going.
Now that's a thought to leave you pondering.
That's the beauty of the universe, isn't it? Always more to explore, more to discover. Who knows what incredible secrets are still out there, just waiting for us to uncover them. That wraps up our deep dive into the Big Bang. I don't know about you, but I'm definitely feeling a bit more cosmically connected today. Thanks for joining us, and we'll catch you next time for another deep dive.